Okay. Pavel, are you ready? I'll introduce you. Is that okay? Pavel, I will introduce you.
Can I share my screen now?
Yes, you can. And I'll introduce you too. Okay. So today, we are very happy and honored to have Professor Pavel Putrov from ICTP, and welcome everyone to this Harvard CMSA seminar on the joint topic of quantum matter, QFT, condensed matter mass, and maybe string theory as well today. So, before begin, let me also mention that maybe two things or two rules. One is that we certainly encourage questions, and I think Pavel also will be happy to take questions. So these are the first thing. The second thing is that we hope to have a positive, constructive, and friendly conversations to improve our understanding. So that's it. So для нас, пожалуйста, чтобы Professor Pavel Putrov предоставил свои исследования. Пожалуйста, спасибо. Пожалуйста, возьмите на себя инициативу. Welcome, Pavel. Please take over.
Okay. Thank you for the introduction, and thank you for inviting me to give a talk. So my talk will be based on a joint work with Atish Devkalkar and Edward Witten. And so let me start by kind of summarizing the goal of the main goal of this work. So the goal is to calculate a certain quantity. So let me write the following formula. So we want to calculate a certain derivative of a partition function of what is called Vafa-Witten theory on CP2. The derivative with respect to tau bar. So let me comment on various ingredients here. So, okay, so this is, as I mentioned, this is a partition function of what is called SU2 Vafa-Witten theory on CP2. And yeah, I will review briefly what it is, but essentially this can be understood as a topologically twisted version of SU2 n equals 4 that is maximally supersymmetric four-dimensional super-Yang-Mills theory. And tau here is a complexified complete constant. Which is a combination of G, the gauge coupling, and the theta angle. Okay, and so there are actually various approaches to kind of deriving, well, to producing the formula for the right-hand side here. But so what I mean here by calculate is the following calculation, is the following particular way to calculate it. So, and actually will be, I will talk about two approaches. So first approach is from the path integral of the four-dimensional theory on CP2. So this is essentially the most direct way to do this. And the second is from the path integral of the two-dimensional theory on T2, which is obtained by compactifying 6D, what is called 6D type A1 2,0 theory on CP2. And this will, I will elaborate on this closer to the end of my talk. And so in principle, so here I'm considering the gauge group to be SU2 and the partition function on a particular four manifold, which is the CP2. But in principle, one can consider generalizations which I'm not going to talk about in my talk, but to make it technically easier. But in principle, we consider we briefly consider this generalization in our paper. So Carler. So first of all, you can generalize it to other Carler manifolds with first Betti number being 0 and B2 plus the number of positive eigenvalues of the intersection form being 1. And you also can generalize it to other gauge groups. In particular, you can generalize it to SUN gauge group instead of SU2. Okay. And so this was brief announcement of what is going to happen. And I will start with a very brief introduction to Vafa-Witten theory. So we want to start with the 4-dimensional n equals 4 superring mills. So the theory has 16 supercharges. And so this theory is completely specified by the choice of gauge symmetry group, which say in general will be G, but later we will want to restrict ourselves to the case SU2 and also SO3 at some point. And it has the following global symmetries. So first, of course, it has spin 4 rotational symmetry. So here we are considering series in Euclidean space. So we have a spin 4 local rotation group, and there will be a global spin 6 arc symmetry, or equivalently SU4 arc symmetry. So this is a symmetry which rotates your supercharges. So spin 4 can be decomposed in the product of SU2 left and SU2 right. And so we want to, so here in spin 6 arc symmetry group, we can take spin 3 subgroup, which is in a natural way just by restricting our rotations to rotation of 3 out of 6 coordinates. And of course, this spin 3 is isomorphic to SU2R. And then so there are different ways to topologically twist 4-dimensional n equals 4 theory. And what we are going to be interested in is what is called a Vafa-Witten topological twist. And this, very briefly, it can be summarized as the following operation. So we want to identify SU2R part of arc symmetry with SU2 left. So more explicitly, what this means is that if you put a theory on a curved manifold, a curved space-time M4, we want to turn on background SU2R connection equal to SU2 left part of spin connection. And what is good about this is that this background, this particular background, preserves 2 out of 16 supercharges on a generic for manifold M4, but it actually preserves 4 on a Keller for manifold. And this is later is a situation which you want to consider. Okay, so are there any questions so far? Okay. So this theory has the following field content. So it will have, of course, it will have a G gauge field, which is locally is realized by connection one form valid in the Lie algebra of G. Then there will be the following fields. There will be a self-dual 2 form and 3 scalars. All of them transforming in a joint representation of the gauge group G. And so these fields, they originate from 6 scalars of the untwisted n equals 4 superring mills. So after the 3, the 6 scalars, the three of them, they just they're still scalars, but the 3 of the 3 they are affected by twisting, and then become a self-dual 2 form, which has exactly 3 components, 3 independent components. Okay, and they also will be the following Grassmann fields. There will be 2 Grassmann scalars. There will be 2 Grassmann valued 1 forms and 2 self-dual 2 forms. And also, again, they all transform in a joint of G. And these fields, they originate from the fermions of untwisted series. Moreover, so our goal will be, so in order to derive the holomorphic anomaly, so the derivative with respect to tau bar of the partition function, what we will need is a realization of supersymmetry of shell. So for untwisted series, it's not know-how to realize all supercharges of shell. But if we just restrict ourselves to the supercharges preserved in this particular background on a curved manifold, it is actually known how to realize this part of this the action of this superalgebra of shell. But in order to do this, it's enough to introduce the following auxiliary fields. So it will be auxiliary 1 form and an auxiliary self-dual 2 form. Again, they also be in a joint of G. So the partition function has the following expected properties, which will be relevant for us. So first property, well, let me write it like this. So the partition function for some gauge group G on a 4 manifold, which also depends on coupling constant tau, is generically non-zero. And so this is actually non-trivial property, because in many cases, what happens after you do topological twist, for example, if you in a Vafa-Witten theory, you get the partition function itself is 0, so it doesn't give you something interesting, But this is usually happens due to Ghost non-trivial Ghost anomaly. But for this particular Vafa-Witten twist, the partition it's valid. The partition function itself is a non-trivial quantity which you can consider. You don't need to do additional insertions to make it non-zero to saturate in Ghost anomaly. And well, the second expected property is what can be called as duality. So if you consider partition function with gauge group G and coupling constant -1/tau should be equal, and by equal I mean up to a certain multiplier system, which I suppress here, multiplier system relative to a certain Hopf anomalies. Which is very easy. I mean, it's very easy to describe this additional place. And for example, if you consider G to be so G hat here is Lagrange dual, and so if, for example, if G is SU2, then G hat is SO3.
Pavel?
Yes.
So are you assuming G to be simply laced here? Otherwise, as duality will transform differently. Will be a factor correspond to the laced T.
There will be a factor corresponding to what?
So I mean, for example, if you're looking at less duality for G2, tau goes to -1/3 tau, right?
Yes. So here I consider G to be simply laced and
okay.
Well, I think you can just focus. The basic element for us will be just SU2 or maybe SUN.
Mm-hmm.
But yeah, so yeah, you consider AD type, and I mean this is related to this 6D picture, which I will talk about. Thanks. Okay, so so the second, so the third kind of expected property, which is kind of naive, and so it will actually fail, is that kind of naively you expect that this this partition function will be holomorphically depend on tau. So the derivative respect to tau bar equals 0. And is there a question?
Why we should expect that? Because the action is real, so we got also complex conjugate tau there.
Well, I will mention in a moment. What? Yeah, I'm just want to write what is the naive argument for this. So the naive argument goes as follows. So if you so this is important. This is for twisted. This is what we consider in twisted theory. So if you calculate the well, if you understand this, the partition function itself as a certain path integral over the space, but let me denote by big phi, a collection of all fields, E minus S, and then the derivative will just descend down the derivative of the action, and then you can just show by using explicit expression of the action, you can show that this is Q, a certain supercharge of something, of some lambda, as sometimes it's called gauged fermion. And so Q here is supercharge, and the supercharge, we know it acts as a derivation in the space of fields. So this integral is always over space of the fields, and then it's so it's a 0 if there is no contribution from infinity. In infinity of the space of fields. So if you go to infinity of the space of fields, there is no contribution. So if you assume this, then this should be 0, just because the dependence of the action on tau bar is Q exact. And so this actually can fail. This actually can fail, and there can be contribution from the infinity, and this is what we want to find. Okay, and so suppose, suppose this is a kind of assumption holds, and moreover, if you impose some additional assumptions, which usually referred as vanishing theorem. So in particular, if you want to be concrete, for example, you can take this vanishing theorem is true when X is scalar, and the first chunk class is non-negative, or equivalently canonical class is non-positive. Then the partition function has nice geometric interpretation. So it can be understood as the following generating function, where generating parameter is Q, and for us always Q is e to the 2 pi I times tau. Of chi of the moduli space of n g instantons on Mn. And chi here is Euler number. So I mean, there is a more general approach for this. So this is more general. This is a generation function of what is called Vafa-Witten invariance. And recently, so if you're interested in kind of mathematical definition of this more general case, so in math, the relatively recent work by Tanaka and Thomas, for example, defines them in case when your four manifold is a projective surface. But let me not go in these details. No. Okay, and so suppose let me denote. Suppose I want to consider what is called naive partition function, which I just try to define by these equations, assuming I have this vanishing theorem satisfied. So in particular, these moduli spaces are actually smooth manifolds, and you can define Euler characteristic in the usual way without doing any virtual environment business. And suppose we use this kind of suppose we try to calculate this partition function using this formula for in the case when for manifold is CP2. And this is actually what was essentially the result for this was provided by in math papers by Yeshoka and Klechko in the beginning of 90s. So so in this case, a naive instanton counting gives the following. So I can write the explicit expressions. for SU2 partition function. Well, let me express it using the functions f0 and f1. So for SU2 partition function will be 1/2 of f0, and SO3 partition function on CP2 tau will be f0 tau plus f1 tau, where fv tau with index v, which takes value 0, 1, is equal to essentially 3 times the generating function of what is called Hurwitz class numbers. So this is what is called Hurwitz class numbers. And eta is a standard Euler eta function. Okay.
I guess it's Dedekind function.
Yes, sorry, yes. Dedekind, yeah, Dedekind, yes.
Sorry, Pavel?
Yes.
For the SO3, I mean, there's a discrete theta angle, so there are 2 different theories. So their Partition function, naive Partition function will just be sum and difference between F0 and F1.
Yeah, so this is just a sum of, this is a discrete theta angle is 0, so it's just sum of, F0 is a contribution of 0 flux,
yes.
And F1 is a contribution of.
Yeah, so it could be sum and difference, I guess.
Yeah, so if you can turn discrete theta angles. So in principle, you can separately consider this F0 and F1, that makes sense. Any other questions? Okay, so suppose we use these naive expressions and try to check if the property 2 holds this S duality. So we want to check if this SU2 naive is equal to SO3 naive SP2. And it's not, but almost. And what almost means is that FV of tau is what is called is a vector valued mock modular form. And this is actually one of the first examples of mock modular forms considered by Zagier. And it has, so I'm not going to go into detail of the theory of mock modular forms, but many of you probably heard about the basic idea. So the basic idea is that it has a kind of non-holomorphic modular completion. So when you replace this FV of tau to FV of tau plus a sort of correction, GV of, which will depend explicitly on as an analytic function on both tau and tau bar. And so this addition makes it modular, and it's such that if you take the limit when, so yeah, unless you consider it's analytic condition with respect to both tau and tau bar, and if you take tau bar with fixed tau to infinity, this goes to 0. But in principle, I mean, they're more systematic way to consider these smaller forms by using the theory of shadows and so on. But yeah, this is not the goal of my talk actually. So, what one can learn from this is that so in particular, so one can find a particular, so there's a particular known expression for these GVs which realize this modular completion. And the anti-holomorphic derivative is given by the following formula. Q bar n plus v over 2 squared. And so if you assume that this correction is indeed the correction which gives you a true physical partition function of Vafa-Witten theory, which we believe in as duality, so it should be, it's indeed respects as duality. So this gives a prediction to what is the to what should be the anti-holomorphic derivative respect to tau bar of the Vafa-Witten partition function. But what we want to do, we want to derive this directly by the methods I mentioned, directly from the path integral in 4 dimensions. So this, this was a very brief summary of what is Vafa-Witten theory and what was kind of the known relevant facts for us. Are there any questions at this point?
Can I ask you a question, Pavel?
Yes.
Okay, so regarding the partition function in math formalism, whether it would be Tanaka-Thomas formalism or our work with Professor Yao, we also gave a DT theoretic version of it.
Yes.
So this tau, just to understand, the one that is going to induce the holomorphic anomaly, this is the one that keeps track of the D0 brane charge of these D branes wrapping the space surface in your language. Am I right?
Well, Q, I mean Q, you mean Q, which is, yeah.
Tau, which is e to the, Q, which is e to the 2 pi I tau. What is Q keeping track of? So in math formalism, the description of these moduli spaces there are 2 versions. One is in Tanaka-Thomas theory. These are moduli spaces of certain Higgs bundles, which have a Higgs map, trace of Higgs map is equal to 0. Or you can also realize these as certain moduli space of D4, D2, D0 branes in a non-compact threefold, which is totally space of canonical bundle of this 4 manifold. But your D4 branes are wrapping the space surface. So all I want to know is this Q, which you're going to use to show us the holomorphic anomaly for. The power of Q is keeping track of, it needs to keep track of certain Chern character for these sheets on the surface.
Yeah,
Is the last Chern character, is this the, for you guys, D0 brane charge, or for us, second Chern character of the sheaf on the surface?
Yes.
Okay. Okay.
Well, here, I mean, you I guess in DT, you also consider, you should consider the generative function with respect to n, kind of rank of your bundle,
yes,
right?
Yes. Yeah. Okay. So do you
here,
have
here the rank is fixed. I fix the rank.
Here the rank is 2, I assume, right?
Yeah, my rank is 2. Yeah. No,
okay.
I don't.
And the first Chern character, which is some kind of codimension 1 cohomology class on the surface, is not going to induce the holomorphic anomaly. But it's the last Chern character, right? It's the second Chern character.
Yeah, the second.
Okay.
But, well, you can include dependence. Like here, just C1 is the first Chern character is assumed to be 0. I mean, you can assume you can consider bundles with varying C1. You can reduce the additional generating parameter for C1. You can do this, but for C2, I'm restricted to just bundles with C1 equals 0.
Okay. Wonderful. Thanks.
In particular, yeah, if you include dependence on C1, you get some sort of Jacobi modular forms. So now, Now, let me start the second part. So the derivation from a four-dimensional point of view. Again, if we repeat, kind of try to repeat this argument about vanishing of the anti-holomorphic derivative, so you end up of having the following expression, where here you integrate over space of fields on CP2. And in principle, you can imagine introducing some particular coordinates. Of course, there will be infinite number of coordinates, for example, harmonics of your field, of all your fields on M4. And so then, if you introduce some, then you can in principle write explicitly your supercharge as a certain vector field or a derivation in this. And then, so what you want to get, if you use a Stokes theorem, so you reduce your integral to integral over the boundary, what I can call boundary at infinity of the space of fields. So this is a measure on the boundary. This was a measure in the original space of fields, and there will be it will be weighted by the product of alpha with n, the normal to the boundary. And you would get E minus S times lambda. So by boundary at infinity, I mean, so there's some sort of infinite dimensional space where your fields live. And so you can consider a certain truncation, for example, a sort of sphere of fixed radius of an infinite dimensional space of fields, and then you want to do this truncation, but later you want to take the radius of the sphere to infinity.
Sorry, Pavel?
Yes.
So this space of fields has no interesting topology?
Well, it depends.
Just some disconnected components, maybe?
Well, yeah. So yeah, the part with the gauge field can have non-trivial topology, but the other fields is just a fine space. But I mean, if for connected components, you just do this for each. So you can do this for each particular connected component, for example.
Right. One more question. So, so as you mentioned, for the Kähler case, there are 4 different supercharges that's preserved.
Yes.
So here, the claim is that for any Q, you can write this Q lambda that gives rise to the derivative with respect to tau r.
Well, I mean, they're not well. There are particular there are various choices of supercharges where you can do this. Yes.
Mm-hmm. But when you do the tau r derivative,
I mean, you can do. I mean, there are choices, but yeah, you can. There is a choice of what Q. Your Q is a linear. It's a certain linear combination of your 4 Qs.
Okay.
Well, when you preserve 2 supercharges, you can take any, but in 4, you have to be a bit careful.
Right, but I just want to make sure. So the supersymmetry that's kind of broken before you add this term is 1 of the 4. Is a combination of the 4.
Yes, yes. It's Q is a particular combination of 4 supercharges.
Okay.
So I mean, you kind of explicitly break some of arc symmetry, but I mean, you can show the result actually doesn't depend on wouldn't depend on the choice which you make. So okay, so this is sounds a bit still kind of not clear how to explicitly do this calculations of the boundary in some weird infinite dimensional space, but which is kind of hard to analyze what is this, but one can make the following observation. So that first, that the non-zero contributions come only from the directions at infinity where only bosonic zero modes go to infinity. So why is this? So this is because the E minus kind of roughly this is because the E minus S is goes exponentially to zero if we take a non-zero mode to infinity, right? And you also don't really worry about the boundary of kind of boundary of Grassmann fields, because there is no, I mean, just because by definition there is no contribution for this. By definition, if you calculate something like this, for where psi is Grassmann integral, this is just identically zero. So this can be, someone can have the following picture in mind. So it will be a finite dimensional space of bosonic zero modes. So this is a finite dimension. And at each point here, there will be a kind of infinite dimensional fiber which contains non-zero bosonic zero modes. All fermionic zero modes. All fermionic, all modes of fermionic fields, and also all modes of auxiliary fields. This is because auxiliary fields they come in action without derivatives. So if you take auxiliary field to infinity, the action will be exponentially suppressed. And so you only so essentially what you want, you're only interested in considering the boundary of this infinite dimensional, finite dimensional space, but then over at each point at this boundary, it's possible just to integrate over these fibers.
Excuse me, I don't know whether it's essential, but as concerns auxiliary fields, why we are sure that the action is positive definite with respect of the terms containing auxiliary fields?
Well, it kind of depends. Yeah, you have to assume. Well, you choose. I mean, you have to see that. I mean, the contour of integration is such that is that it's will be the action will be kind of positive. I mean, the E minus S will be.
So we have to change the standard reality conditions of the fields, right? Or not?
Well, you choose. Well, it depends. I mean, either you choose. I mean, it depends how you introduce a auxiliary field. So if you introduce like you can redefine it by introducing some I, and then or you can say that the contour of integration is such that it's exponentially suppressed.
But doesn't it create a problem when we integrate out the auxiliary fields? Then we will be left with the complex action. Isn't it bad?
Well, I mean, here this after as a topological twist, I mean, the theory is not only unitary, so I don't think it's a problem.
Mm-hmm. Okay, thank you.
Okay, so so in particular, if we consider our example CP2, so the bosonic fields which are not auxiliary, they are either fields which come from this twisting of the scalar theory or the gauge field. And on CP2, we know that there is no flat connection. There will be no zero modes. No zero modes for the gauge field because there is no non-trivial flat connections. And so all bosonic zero modes they originate from the scalar fields of the untwisted theory. This means so if you're interested in considering theory, so in the contribution from this boundary in the space of bosonic zero modes, so this is so this comes from contribution where the scalar fields are kind of fluctuate over some large mean values, and this means so in this description we can effectively describe use description of the theory on the Coulomb branch. So near the infinity of the space of bosonic zero modes can use effective description on Coulomb branch. This gauge group spontaneously broken to U1 subgroup of SU2. And so we can so in a sense we integrate all we can integrate out in this in near the boundary, we can integrate out all W bosons and their superpartners to get effective theory described by just U1 gauge field and their equals to superpartners, but with a certain effective action. So one can consider the derivative expression of the effective action. So in the two derivative part, there will be just a free action of n equals 4 U1 Maxwell theory. And on the 4 derivative level, there will be a certain term, which is, let me denote by this, n equals 4 WZ, which can be understood as n equals 4 completion of a certain Wess-Zumino term, which I will write in a moment. And there will be also further corrections, which will be, one can argue that they will be suppressed at this boundary in the space of field, so they are not going to contribute to our result. So that's the minor term which I mentioned here. So it was obtained in particular in paper by Zeitlin Zaremba in '99, and also was considered by in Trilligator in 2000. And so what we actually want to n equals 4 completion of this term. But the minor term itself can be written as follows. So since the minor term, it's written in terms of integral of a certain phi form over 5-dimensional space-time whose bound, so that our 4-dimensional space-time lives on the boundary of this 5-dimensional space-time, and there will be there will be supersymmetric the supersymmetric completion, which actually we want to find, which will be relevant to our holomorphic anomaly. So, first, let me make a few comments on this minor term itself, the bosonic one. And so the coefficients in front is a number, and W is a number of W bosons, which is a difference between the dimension of the unbroken gauge group and U1, which is just 2. And so in untwisted theory, with the general background spin 6 connection, it can be written as follows. So suppose, so let me denote by phi a goes from 1 to 6, the scalars of the 6 scalars of the untwisted theory, and by phi a hat denote the normalization by the norm of this 6 vector. So this can be understood, the phi hat can be understood as valued in a unit 5-dimensional sphere. And then one can also introduce the covariant derivatives, which is well, covariant differential, which is differential field phi hat A plus the component AB component of the spin 6 asymmetry connection times phi hat B. And okay, using these notations, one can write explicitly what is this eta 5, the phi form eta 5, which enters in this interaction. So one can, in principle, formulate it more invariantly as a pullback of a certain, or pullback of what is called earlier angular form. But let me just write an explicit expression which one can use. So F R is a curvature of the spin 6 connection. In any case, it's a certain phi form constructed constructed from the scalar fields and the SO6 asymmetry connection. So let me make a few remarks. What is the physical meaning behind this term? So first, this term can be understood as a term which you need to compensate the mismatch between the SU4 asymmetry Hooft anomaly on the Coulomb for U1 gauge group and SU2 gauge group. So this can be seen as follows. So, okay, let me write the following. This term compensates the mismatch of SU4R Hooft anomaly. So if one considers the general kind of gauge group G n equals 4 super young Mills, its anomaly polynomial contains the following degree 6 anomaly polynomial contains the following terms: the dimension of a group G divided by 2 times the third term class of SU4 R symmetry bundle.
So you're saying SU4 R symmetry and you wrote SU2 R symmetry. Is that a typo?
Yes, yes, a typo. Thanks. Yes, it should be SU4. The full. Yeah, here we're considering the full. Yeah, here the consideration is before twisting, so we consider the full. There's some general SU4 symmetry background. So the way, for example, to see this is that so these phi hats. So one can consider. So let me briefly tell you how to see this. So one consider a S5 bundle over your sigma 5. So this is this extended space-time. So the total space, let me know, by E, and then phi hat. So phi hat here can be understood. The phi hat field before can be understood as a section of this bundle, and let me know by P the projection. And so this S5 is S5 on which SO6 R symmetry acts. And then this eta 5 form can be understood as a pullback of a certain form E5 on the base. Pullback to the base of a certain to our spacetime, also certain form on a total space, such that its differential is equal to pullback from the base to the total space of the Euler class of SO6 R bundle, which is the same as third term class of SU4. So this kind of just a remark of kind of so this this term is really constrained by anomalies. And the second remark is that so we want to actually consider the n equals 4 completion of this Weserminer term. And so if you consider this completion and we reduce it to just consider its restriction on just n equals 2 vector multiplet, which is a part, n equals 2 vector multiplet, which is a part of the full n equals 4 vector multiplet. So this term, the corresponding term was actually considered in the paper by Diane Zyberg in '97, and it can be so if I denote this the superfield by psi, it can be written as follows in the superspace. But again, it doesn't contain all the information, all n equals 4 supersymmetrization, which actually we need to derive the Holomorphic anomaly. So there's still some work that needs to be done to do a supersymmetrization.
Has this been done? Is the n equals 4 completion of this term known?
in certain like bosonic, the full bosonic part is known, but it's not, again, for us, it's not enough. We need actually the term which contains fermions, the fermionic terms of the analogous form. So in principle, no, it's not known.
Which terms are needed that are not so easy?
Well, so one thing, well, I mean, the fermionic terms, which there can be terms, for example, quadratic and fermions, which actually vanish if you just restrict to n equals 2 vector moduli, and you cannot rotate. You cannot rotate them just to n equals 2 vector.
But why is it so hard to work it out in components? Isn't it a straightforward calculation?
Well, so okay, let me point out the point. So what we actually need, we want this off shell. We want this off shell. And for off shell, n equals 4, as if n equals 4, off shell is actually known to do. Not know how to do.
Why do you need it off shell? Can just complete this term on shell. This is a finite number of terms, I believe, that would make it n equals 4 invariant on shell. That looks to me like a straightforward exercise.
Well, you can, yeah. Well, yes, but this has not been done. Even like including like bosonic part, full bosonic part on shell, it was done in some papers, but including fermions, this has not been done on shell.
Thank you.
I mean, this is doable again, but this hasn't. I mean, to my knowledge, this has not been done. Okay, so this was just remarks about the about this term. And okay, so now we want yeah, we can proceed first. So as a so as contributions from, so I'm gonna make the usual argument as a contribution from non-zero modes in the path integral cancel due to supersymmetry. So I'm going to reduce the integral to a finite dimensional integral over the zero modes. Okay, so what is the zero modes on CP2? So it's straightforward to. So now we're just considering U1, so U1 gauge series. So let me come back to the field content and just do this counting, which is really easy to do. So on CP2, you want to count zero modes on CP2. So there will be, again, there is no float connection, so there will be no zero modes from gauge fields. So there will be there is one cell dual 2 form on CP2 since B2 plus equals 1. There will be one zero mode from cell dual 2 form, and there will be of course three zero modes from 3 scalars, and there will be 2 Grassmann zero modes from scalars. Again, no zero modes from 1 forms, and there will be 2 zero modes, one from each cell dual 2 form. Again, because B2 plus equals 1. Again, there will be no auxiliary zero mode from 1 form, and there will be 1 auxiliary zero mode from cell dual 2 form. Okay, so this was the counting, and to summarize it here. So there's a 4 bosonic zero modes, which is it's useful to organize them in a 2x2 matrix where A and A bar run over 1 and 2. So this can be sort of kind of spinor indices. There's actually considered spinor indices of an unbroken unbroken spin 4 R symmetry, which is unbroken on Keller manifolds. And there will be 4 Grassmann zero modes. Chi A, let me know this by Chi A and Chi bar A bar. There's the 4 independent Grassmann variables, and there will be 1 auxiliary zero modes, which means denoted by H. And then, so everything reduces to just a finite dimensional integral over the space of these zero modes. Okay, there will be a certain factor eta to the power, which is the Euler characteristic of CP2, which is just 3. So this contribution can be understood as a contribution from point-like instantons and okay, there will be sum over n. So n here is a fixed flux of a U1 gauge field in CP1 inside CP2. And there will be a certain numerical constant. And then you integrate over U's, 4 bosonic zero modes, 4 fermionic zero modes, 1 auxiliary zero mode. And then you essentially consider the previous expression as before, but you take everything zero modes. So the Q of zero modes acting on lambda restricted to zero modes, E minus S restricted on zero modes. And one can write in principle everything explicitly. So again, this action is restricted to zero modes. The relevant pieces for us will be the free part of the action restricted to zero modes, and this will be just given by the following expression. So it will be part quadratic in auxiliary fields. So 4 pi n and the flux n, 2 pi I tau n squared. So remember the n is the flux of the gauge field on CP1 inside CP2. And the zero mode restriction of this n equals 4 completion of the with the minor once you do this, once you find the completions in this using off-shell supersymmetry, and you restrict it to zero modes, you get the following expression. This is just to point out that everything is very explicit here. And so, for example, lambda restricted on zero modes is given by the following expression. So again, for lambda, you break this asymmetry even further, because what you do, you choose. I mean, you want to choose a particular supercharge out. I mean, some particular linear combination of 4 supercharges. I mean, to do an explicit calculation. And so this Q, the supercharge is just, it becomes a derivation in this finite dimensional space. And so you just plug this in, all these components in the integral before, and you evaluate one-dimensional integral, and you end up with this with the expression. So suppose I calculate it for CP2 in particular for simplicity, but in principle you can do this for SO3 with a fixed discrete flux as well. So indeed you get the expression predicted by the mock modularity. And well, in order to, well, let me briefly kind of explain what kind of important part of this derivation. So there are four fermionic zero modes, and you need to get something to get non-zero derivation. You have to saturate all four of them. So one fermionic zero modes will go away once we use a Stokes theorem for Q derivation. So this takes away one of the fermionic zero modes, and then another fermionic zero mode will be consumed by lambda, and what is left there are left two fermionic zero modes, and they will be consumed by this term in the this Wierzemina action supersymmetrized, which is quadratic in fermions. And this gives you saturation of all four fermionic zero modes. So this was a derivation from four-dimensional perspective. Are there any questions at this point?
So I have a question. So for the for the Western term, if you just know the bosonic contribution, can you fix the fermionic contribution using the Q invariance without deriving the Lagrangian, which presumably is very complicated?
Well, you can fix, well, you still need to fix the bosonic contribution, which, well, essentially you want to fix a bosonic contribution, but which includes also auxiliary terms. And then you can, well, you can already, I mean, there is a residual supersymmetry acting on Jacksonian space of zero mode. So it's enough actually to get this, for example, it's enough to get this part of the restriction to zero modes. And then you just, this is fixed by this, by just like supercharges acting on a finite dimensional space.
Right, so the part that you just circled is the one coming from like 1/phi to the fourth and then box square acting on phi, right? I mean, box phi squared. So U is coming from the scalar?
U comes from phi, from the scalar fields.
Right. So that's the goldstone. I mean, it's the dilaton, right?
Well, okay. Let me. So in the not on zero modes, you have an action something like this. So this part from the part of the action which is of Fr, which is the background curvature for background asymmetry. Then you have well, suppose I consider this term. Well, there is a kind of suppose I consider this times this part. Then there will be the curvature, the gauge field strength, the curvature of the gauge connection, and then there will be auxiliary term, and then there will be some function of well, some function of scalar field, but it's roughly something like phi divided by phi squared.
I see. So you say it's the mixed terms involving both dilaton and background contributes, not the the terms that just involve the dilaton because they're zero modes. Okay.
Yeah. For example, all this bosonic term which I wrote on is just itself goes to zero because they're derivatives of scalar.
That's right. That's right. Yeah.
So I have a question. If you do this for a manifold with B2 plus bigger than 1, then we should be able to see explicitly from this kind of description that there are too many fermion zero modes and you do have a holomorphic partition function.
Yeah, so you have too many fermionic zero modes which you cannot saturate, so you just get zero.
But I was hoping you could show us in the context of this kind of calculation.
Well, I mean, you still like the counting of this. I mean, not here. Still you have two kind of this sugarized two Fermi Zermos and this sugarized two Fermi Zermos. But the number of integrals will increase because as we count it, the number of zero modes they will increase. Fermi Zermos will increase when B2 plus is greater than 1. So roughly, yeah, the argument is like this.
What's not obvious is that the Vesamino term doesn't also produce enough fermionic couplings that you'll still be able to soak up the larger number of zero modes when B2 plus is bigger than 1.
Well, they will be, in principle, they can be, but they will be suppressed. They will be there will be high power of U downstairs.
So what? If U, so what? That's a Gaussian integral in U. I don't see how power of U is going to help.
Well, in this, so you actually, if you restrict to this, let me. So, for example, if you consider the super partners in this particular, there is actually no, you can show in principle you can show explicitly there will be no, like for example, no 4 fermion term. So in principle you can naively write this 4 fermion term, but you can see that it will be just it will actually be absent for some reason. I mean, it's not like. I mean, you can argue that it's actually 0. It's not obvious. In principle, we can assume that there is 4 fermion zero modes. There is a term which is proportional to 4 fermions in this.
Okay, yeah, it's really not obvious that. I mean,
it's not obvious, but yeah.
4 and 6 fermion zero modes up in the Vesamino term, because we do expect, of course, it to be holomorphic when B2 plus is bigger than 1.
Yeah, but I mean, we do show that there is like you can make an ansatz like for just all of zero modes. You can make an ansatz which contains the 4 fermion part, but then can show that this like in the supersymmetrization of for this particular kind of scaling properties which have the Vesamino term, then you don't have 4 fermion zero. I mean, we didn't yeah. We didn't consider this in detail for B2 plus equals 1, but this is, yeah, we just consider for CP2, but in principle, yeah, you can extend this for B2 plus equals greater than 1. Any other questions? Okay, so if there's no other questions, so let me just very briefly mention the other way to derive this. So essentially, we use the fact that the SU, we can use the fact that SU2 for the superrank mills on M4 is the same as 6D 2,0 series of type A1 on M4 times T2, and for example, the coupling constant plays the role of the complex structure parameter of the torus. And then using this relation, you can interpret the partition, the Vafa-Witten partition function as, so let me write as a worse as elliptic genus or T2 partition function with T2 with odd spin structure. Of the effective to the theory T of M4. The theory is usually denoted by T of M4, but it also depends on the choice of ADE choice of your 6D theory. And so in general, so this here, by elliptic genus, I mean the kind of the physical elliptic genus, which is this T2 partition function, and which is more explicitly can be written as a trace of -1 of the f over the Hilbert space on a circle, q to the L0 and q bar L0 bar, where L0 and L0 bar, they are left and right moment Hamiltonians. H is a Hilbert space on a circle. And then by the usual argument, one can show that if the spectrum is discrete, you can argue that if theory has so in general, so if we talk about general two-dimensional series, if theory has right moment supersymmetry, and this is the case of this effective theory T of M4, and if spectrum is discrete, so the elliptic genus is holomorphic in tau, and this is given by the usual argument that when the contributions from the states where L0 bar is non-zero, they cancel out because of the supersymmetry, the cancellation between fermions and bosons. This is the usual argument. And but what can happen if the spectrum is not discrete, for in particular, if you series something like a sigma model with non-compact target, this may not be the case. And this various examples of this we studied in the literature already for some time. And so this can fail in, for example, in sigma models with non-compact target. So one of the first works about, probably about, yeah, I'm not gonna give all the references. It was by Trusti, Gucci, Sugawara, Mercy, and many others. But what I want to mention also is a relatively recent paper by Gayotto and Johnson-Frade, which makes the following statement in particular. So if you take sigma of x, let me denote to be sigma model with at least 0, 0,1 supersymmetry. So there at least one supercharge in the right moment sector with target x. So this means boson, we have bosons in the maps from worksheet sigma to x and right moment fermions. So roughly they live in a kind of they're valued in the tangent bundle, but to be precise, so the sections of the pullback of the tangent bundle tensored with right moving spinor bundle on sigma on the worksheet. And then, so Gayotto, Frade, Johnson, they argued there should be the following formula. So if you consider the this partition function of this so elliptic genus or partition function of the sigma model on T2, its holomorphic anomaly is given by the following formula. There's a certain factor. And here we have the following correlation function. So this is a one-point function of supercurrent G bar on T2, or not again on the two torus in a sigma model with target being the boundary of the original target X. So again, this is a boundary at infinity. And so if you wish, there's explicit expression for the supercurrent in the sigma model. So they actually make the statement more general, not just in sigma model, but consider this for sigma model. It's the easiest to understand this. And so the supercurrent has the following expression, particular expression in terms of the fields of our fields phi, the bosons, and psi, the Riemann fermions, where this is just metric on target and on X or on the boundary, and this is Vafa-Witten 3 form. So the 3 form in the target, which defines, which is used to define the Vafa-Witten term. Okay, and so the point here is that so one can essentially use this use this formula to well, up to some subtleties, one can use this formula to derive the holomorphic anomaly using this 4D2D correspondence. And so if we use, again, by the same argument, one can go to the tensor branch. So before we went to the Coulomb branch of n equals 4D series, here we can, by some argument, you can go to the tensor branch of the 6D series. So using the description of 6D series on the tensor branch, we can get a effective description of the series TFM4 by reducing by compactifying this description of the tensor branch. So result is that this T of M4 is almost, and I say what almost means, almost a sigma model with target, supersymmetric sigma model with target of the class I considered before, of the with the target X being R cubed times S1 divided by Z2, and almost means that the boson valued in S1 is chiral. And okay, so the boundary of this is S2 times S1 divided by Z2. So Z2 acts by flipping all the coordinates. So, and this comes from the Weil symmetry. And with, and they also, there's a Vafa-Witten form, 3 form. Well, on the boundary, if you on the boundary, it just has the following expression. So it's 8p squares times 3 times the volume, the unit volume form on S2, which is the unit volume form on S1. And so the origin of this, the 6D origin of this Vafa-Witten 3 form is the following term in the 6D action. It's a B, which is a self-dual. It's a self-dual to form, which is a part of the tensor multiplet, which you have on the tensor branch, and eta 4 is the analog of form eta 5, which is constructed not the eta 5 was constructed from the 6 scalars of 4-dimensional CA, and similarly you can construct this analogous form eta4 from the 5 scalars of the tensor multiplet. And okay, and using the formula above, so the calculation of this 1-point supercurrent in this theory with the target dx gives again the same expression for the holomorphic anomaly as before. Okay, so
where do the overall powers of eta come from?
So the overall power of eta comes from the essentially from the non-compact from the bosons from the bosons
from the R3 bosons. But I thought you were evaluating a signal model on the boundary. So I'm confused.
Well, you also have one of eta from the you have character, this S1 chiral boson is essentially U1 with the Mino model. And you have
that's one power of eta. You need 3 of them.
Yeah, 2 powers come from this guy. Okay. There will be S2, which is well, the S2 is very large. So semi-classically, it's just it's a two free bosons, but you normalize them kind of you in the regularized Pfeiffer volume. So there will be 2 powers of eta from S2. And 1 power of eta from this guy.
And the twisted sector in the Z2 orbifold doesn't contribute? You're taking an orbifold by Z2?
No, not really, because well, you just it effectively just reduces your result by 2. Again, like the part where S2 is really large.
Oh, it's a free action.
Like, and each point, like you consider as like sigma model in the largest limit of S2, and this chiral S1 is just contribute to each fiber, like in this large radius sigma model. So the Z2 is just gives you essentially 1/2 factor in the integration. So yeah, so yeah, the kind of the Partition function of this guy is, of the S2 part, it just gives you something like volume of S2, which you want to divide by 2 because of the Z2 divided by eta and tau. And this gives you this character of E1, well, level 2 with the Vafa-Witten. See.
Why does the actual partition function give you class numbers?
Well, from this point, I mean, yeah, we don't have explanation for this. So this is really a derivation of only derivative. I mean, there is no, I don't know if there is some kind of canonical way to reconstruct the holomorphic part knowing the derivative. I mean, you have to make some additional assumptions. Yeah, I don't know how to see Hurwitz class numbers from this approach. But here is where I stop. Yeah, that's all I wanted to say. Thank you. But if you have questions, please.
Thank you, Pavel. Please feel free to ask questions.
Sorry, probably very simple question, but I don't understand how it can appear. How it appears that the index of theory is holomorphic function if the target space, for example, is compact and spectrum is discrete, because there is L0 bar, so it acts trivially. There are no modes charged by it, or how? We take a chiral piece of model.
Well, this is I mean, the case when you have a, well, suppose you have sigma model with right moment supersymmetry, like you had this right moment fermions living with Einstein. Then again, but I mean, this is true for any for any theory with kind of well, with some condition on the spectrum, well, roughly speaking, it should be discrete spectrum, so that you always have like all contributions when from the states when L0 bar is non-zero, they cancel out because of supersymmetry. So you can just write it essentially I mean, essentially you want, I mean, you can reduce this trace to the trace of a BPS sector, but without with this removed.
But naively, the theory is symmetric with respect to Q bar replacement.
No.
How?
No, because I mean, it's not symmetric because you have a well, L0 and L0 bar, they are left and right moving. They are left and right moving Hamiltonian. So L0 is something like H plus P. H is a Hamiltonian, P is momentum, L0 bar is H minus P. And I mean, your matter content is well, your field content is not invariant on the change of chirality because you only have right moving fermions, but you don't have left moving fermions.
Ah, sorry. Yeah, the sigma model is 1,0. So sorry.
0,1. Yes.
Yeah. Okay.
Yeah. If the theory has right moving supersymmetry.
Sorry. Yeah.
Can I ask a question?
Yes.
Can you say briefly how does the derivation change if you consider the higher rank case? So, for example, do you have more? I mean, is there still a single, four-degree term that you need to care about, or there are more terms you need to consider on the Coulomb branch?
Well, essentially, you need to consider the same. I mean, this is quite analogous. So you consider the breaking in a sense that you consider breaking of SUN, for example, to.
Or you do it step by step, or you consider okay, you do it step by step.
You kind of get some sort of recursive relation in a sense. So we consider breaking of SUN, where n1 is to SU and 2, and then. So you can write the relevant term will be again the term which is just for this U1 abelian part.
Right.
And then the result will be expressed using this U1 like U1 gauge theory and SUN1 gauge theory and SUN2 gauge. But yeah, right. I mean, well, using this one. But then you can first obtain holomorphic anomaly on these guys again, and you can kind of obtain this kind of recursive relation.
Mm-hmm.
So what you get expression, or you don't get an explicit formula for the derivative with respect to bar, but you get expression with a holomorphic anomaly in terms of kind of partition, in terms of partition function of SUN1 and SUN2.
Right. So maybe a not so related question, but so the holomorphic anomaly I can think about it as a tension between supersymmetry and S-duality, correct?
Well, yes, yeah, I think.
Yeah, and then from the 6D perspective, it will be just a tension between supersymmetry and large diffeomorphisms.
Supersymmetry. Well.
Because SO2C would act by a large diffeomorphism on the T2.
Yes, I mean also in 2D, you can say it that way.
Right. So does this help to to derive this this anomaly from the 6D perspective? I mean, by combining knowledge of this large gravitational anomalies.
This would be more like, I think it would be more like this argument prediction using mock modularity. So here we really want to see how the holomorphic anomaly comes from the not like by adding, we don't want to like add try to see what non-holomorphic piece we want to add to cure this large diffeomorphism symmetry. What we want to explicitly see how this comes from some non-compactness.
Right.
So yeah, I think it's a bit different.
But you can, instead of adding this non-holomorphic piece to cure that SL2Z duality, you can insist on supersymmetry, and you will have this SL2Z anomaly.
Well,
I was just asking if
but I mean, for physics, the kind of the SU2 symmetry is more fundamental than the holomorphicity. So you actually, I mean, you still want to like SL2Z, you still want. I mean, it should be there, but this holomorphicity can fail. Again, the holomorphicity is kind of okay, it's related to supersymmetry, but under assumption that the everything is nice and compact.
Well, I was just saying that there's some regularization scheme you can choose. So it's like a counter-term ambiguity. In one case, you can insist on supersymmetry being preserved, even in the presence of these non-compact directions on the moduli space. In the other case, you can insist on having SL2Z preserved. I mean, for example, in the case of just Maxwell theory, I mean, it has a SL2Z anomaly, right? In discussing Witten's paper.
Maybe, I don't know. Yeah, I haven't thought about this this way of thinking.
Thanks.
Any other questions?
Well, in any case, let's thank Pavel for the very nice lecture and talk. Thank you very much, Pavel. Большое спасибо. Thank you.
Thanks.
Thanks.
If people still have a question, they can ask more.
Thank you.